Right now, there might be another version of you doing exactly the same thing. Not somewhere in our universe. That other, you would be so impossibly far away that the number describing the distance would have more digits than there are atoms in the observable cosmos. We're talking about 10 to the power of 10 to the power of 29 meters. That's a 1 followed by 10 billion 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 zeros. And not just one other you. If certain equations in physics turn out to be correct, there could be infinite copies of you. One where you chose a different breakfast this morning. One where you never learned to read. One where humans never evolved at all. Infinite variations, all equally real, all completely unreachable. This isn't science fiction. This isn't mysticism. And critically, this isn't proven fact. But it's what some of the most brilliant physicists alive today think might be true. And here's what makes it so unsettling. They didn't go looking for this idea. They didn't sit around trying to imagine the strangest possible reality. They were working on completely mundane physics problems, trying to understand the early universe and the behavior of atoms, and the mathematics kept dragging them toward this conclusion, whether they liked it or not. This is the multiverse hypothesis. Multiple universes. Parallel realities. An existence so vast that everything we can see, every galaxy in every direction, might be just one tiny bubble in an infinite cosmic foam. And what we're going to explore over the next 2 hours isn't whether this is definitely true. We don't know that. What we're exploring is why serious scientists take this seriously, what the different versions of this idea actually propose, and what it would mean for our understanding of reality if any of it turns out to be right. Let's start with the most important question. Why would anyone believe in something as wild as the multiverse? Scientists are supposed to be skeptical, evidence-driven, conservative in their claims. So why are some of the smartest people in physics entertaining an idea that sounds like it belongs in a comic book? The answer is surprisingly straightforward. They're not choosing to believe in the multiverse. The multiverse keeps emerging as an unwanted consequence of theories that were developed to solve real, concrete problems. Think about it like this. You're a detective investigating a crime. You gather evidence, follow leads, build a case. And then your investigation keeps pointing toward a suspect you really don't want it to be. Maybe it's someone you know. Maybe it's someone whose guilt would create all sorts of complications. But the evidence doesn't care about your preferences. It points where it points. That's roughly what happened with the multiverse. Physicists were investigating different puzzles about the cosmos and about quantum mechanics, completely separate investigations. And multiple independent lines of inquiry kept pointing toward the same uncomfortable conclusion. Our universe might not be alone. Let's look at the specific problems that led here. Problem 1. The early universe. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see something puzzling. The temperature is almost exactly uniform in all directions. It varies by only a few parts in 100,000. Why is that strange? Because regions on opposite sides of the sky are so far apart that light hasn't had time to travel between them since the Big Bang. They've never been in contact. They couldn't have influenced each other. So why do they have the same temperature? Back in 1980, a physicist named Alan Guth proposed an answer called cosmic inflation. The very early universe, he suggested, went through a brief period of exponentially rapid expansion. A region smaller than an atom inflated to larger than a grapefruit in a tiny fraction of a second. This solved the temperature problem beautifully. Regions that are now on opposite sides of the observable universe were once close together in thermal contact before inflation separated them. Inflation worked so well that it became mainstream physics. It explains multiple features of the universe we observe. The evidence supporting it keeps getting stronger. But here's the catch. When physicists worked out the mathematics of inflation in detail, they discovered something unexpected. In most versions of the theory, inflation doesn't just happen once and stop everywhere simultaneously. It's eternal. It keeps creating new regions, new pockets, new bubbles of space. Our observable universe would be just one bubble in an eternally inflating cosmos. The physicists didn't want this result. It complicates everything. But that's what the equations said. Problem 2. Quantum mechanics. This is the theory that describes the behavior of atoms and subatomic particles. It's the most successful scientific theory ever created in terms of experimental confirmation. The predictions match observations to absurd precision. Quantum mechanics is the foundation of modern technology. Your phone, your computer, medical imaging devices, lasers, all of it depends on quantum physics being correct. But quantum mechanics has always had a conceptual problem at its heart. Before you measure a particle's position, it doesn't have one. It exists in what's called a superposition, a fuzzy quantum state where it has some probability of being here and some probability of being there. Only when you measure it does it snap into a definite location. This leads to the famous measurement problem. What counts as a measurement? When exactly does the superposition collapse into a definite state? Why does observation seem to play this special role in physics? These questions bothered physicists from the beginning. In 1957, a graduate student named Hugh Everett proposed a radical solution. What if the superposition never collapses? What if all possible measurement outcomes happen, but in different branches of reality? When you measure a particle that could be spinning clockwise or counterclockwise, the universe splits. One branch gets clockwise, another gets counterclockwise. Both are real. Everett wasn't trying to invent parallel universes. He was trying to take quantum mechanics seriously, to apply it consistently without adding special rules for measurement. The branching multiverse fell out of the mathematics when he did that. Problem 3. The constants of nature. Why does the electron have exactly the mass it has? Why is gravity precisely as strong as it is? Why does empty space have the tiny energy density we measure? These fundamental constants seem arbitrary. You can't calculate them from deeper principles in our current theories. You measure them and plug them in. But here's what's strange. If you change most of these constants even slightly, the universe becomes lifeless. Make gravity a bit stronger, and stars burn out too quickly for life to evolve. Make it weaker, and stars don't ignite at all. Adjust the strength of the electromagnetic force, and atoms don't form. The universe seems fine-tuned for complexity and life. This fine-tuning bothered physicists. Some saw it as evidence of design. Others hoped to find a unique theory that would predict exactly these values and no others. But there's a third possibility. If there are many universes with different values of the constants, we inevitably find ourselves in one where the constants allow life. Not because our universe is special, but because we couldn't exist in the others to observe them. String theory, an attempt to unify all forces and particles, ran into this issue. Instead of predicting one unique set of physics, the theory seemed to allow for an enormous number of possibilities, maybe 10 to the power of 500 different configurations. Each would give different constants. Physicists called this the landscape. And if eternal inflation is real, different bubble universes might sample different parts of this landscape. Again, this wasn't the goal. String theorists wanted a unique prediction. They got a vast multiplicity instead. So we have three independent problems: the early universe, quantum measurement, and fine-tuning. Three completely separate areas of physics, and all three point towards some version of a multiverse. That's why physicists take it seriously, even though it sounds absurd. It keeps showing up where they're not looking for it. Does this prove the multiverse exists? Absolutely not. The theories that predict it could be wrong or incomplete. The interpretations could be flawed. Maybe there are better solutions we haven't discovered yet. But it explains why this isn't just wild speculation. It's a hypothesis that emerges from our best attempts to understand real phenomena. Now that we understand why physicists consider this at all, let's look at what they actually mean by multiverse. This isn't one simple idea. There are several distinct versions, each stranger than the last. The physicist Max Tegmark organized these into 4 levels. Each level represents a different type of multiverse based on different physics. Let's walk through them. This is actually the simplest version, and it doesn't require any exotic physics. It just requires the universe to be infinite in spatial extent. If space goes on forever in all directions, and if the laws of physics are the same everywhere, then something interesting happens. There are only so many ways you can arrange atoms in any given volume of space. The number is enormous. If you take a region the size of the observable universe, the number of possible arrangements of all the particles in it is roughly 10 to the power of 10 to the power of 120. That's incomprehensibly large. But it's finite. If space is infinite, those arrangements must repeat. It's not a matter of probability or chance. It's mathematical certainty. Just like if you shuffle a deck of cards forever, you'll eventually get every possible sequence and then start repeating them. So if the universe is infinite, then somewhere, unimaginably far away, there's a region of space with exactly the same arrangement of particles as the region you're in now. Same planet, same people, same you, reading this same script. And not just one such region. Infinite copies. How far away would this duplicate region be? Given the number of possible quantum states in a volume the size of the observable universe, your nearest identical copy would be roughly 10 to the power of 10 to the power of 29 meters away. To put that in perspective, the observable universe is only about 93 billion light-years across. That's roughly 900 trillion meters. Your duplicate is so far away that the observable universe looks like a subatomic particle by comparison. But here's the thing. These other regions aren't in separate universes. They're in the same universe as you, just unreachably far away. Light from those regions will never reach us because the expansion of space carries them away faster than light can travel toward us. So even though they're technically part of the same cosmos, they might as well be in different realities. Does level 1 exist? We don't know. It depends on whether the universe is truly infinite. We can measure the curvature of space to see if it curves back on itself like a sphere, which would make it finite, or if it's flat, which allows for infinity. Current measurements say space is extraordinarily flat, consistent with being infinite. But we can't measure far enough to know for sure. The important point is that if the universe is infinite, level 1 multiverse exists as a mathematical consequence. You don't need to believe in any new physics. You just need infinite space. This one comes from taking inflation seriously. Remember, inflation is the rapid expansion of the very early universe, and it's supported by strong observational evidence. But when you work out the mathematics, most versions of inflation don't stop everywhere at once. Imagine a field permeating all of space. In regions where this field has high energy, space inflates rapidly. Quantum fluctuations cause the field to drop to lower energy in some spots. Those regions stop inflating and become pocket universes like ours. But in the regions still inflating, space expands so fast that even as pockets stop inflating, the total volume of inflating space actually increases. It's like boiling water. Bubbles form and separate from the liquid, but the boiling process continues producing more bubbles. In eternal inflation, our observable universe is one bubble. There are countless others, forever being created in the inflating space between them. Now here's where it gets interesting. When each bubble forms, the field driving inflation settles down in slightly different ways. This is called symmetry breaking. Think of water freezing into ice. Liquid water looks the same in all directions. But when it freezes, the molecules lock into a crystal structure pointing in some particular direction. Different regions of ice can have different crystal orientations. Something similar might happen with the fundamental forces and particles. As each bubble universe cools down, the symmetry breaks differently. One bubble might end up with gravity slightly stronger than ours. Another might have electrons that are heavier. The fundamental constants of nature could vary from bubble to bubble. Most bubbles would be lifeless. Change the constants even slightly, and chemistry doesn't work, stars don't form, complexity is impossible. We find ourselves in a bubble where the constants allow life, not because we're special, but because we couldn't exist in the lifeless bubbles. Is eternal inflation real? The jury is still out. The basic inflation model has strong support. Whether it continues eternally is less certain. It depends on details of the inflaton field that we don't fully understand. But if inflation is correct, and if it has the properties that most models suggest, eternal inflation and level 2 multiverse would follow. This is the many worlds interpretation of quantum mechanics, and it's probably the most philosophically challenging version. Quantum mechanics says that before you measure a particle, it's in a superposition of states. An electron can be spinning both clockwise and counterclockwise simultaneously. Only when you measure it does it become definite. The traditional interpretation, developed in Copenhagen in the 1920s, says that measurement causes wave function collapse. The act of observation makes one outcome real and the others disappear. This works for making predictions, but it's conceptually troubling. It seems to give observation a special status in physics. What counts as an observation? Does consciousness play a role? Where exactly does the boundary lie between the quantum world and the classical world we experience? Hugh Everett's many worlds interpretation offers a different answer. The wave function never collapses. All outcomes happen. When you measure that spinning electron, the universe branches. One branch has you observing clockwise spin. Another branch has you observing counterclockwise. Both versions of you are equally real. Both convinced they got a definite result, but you're now in separate branches that can never interact. This happens constantly, everywhere, at every quantum event. Particles decay, photons get absorbed, quantum states interact with their environment. The universe is branching trillions upon trillions of times per second. The number of branches is beyond comprehension. Is many worlds correct? A 2025 Nature survey of physicists showed around 17 to 20% favor it, making it one of the more popular interpretations, though still behind the Copenhagen interpretation. But it remains controversial. Some find it elegant, because it doesn't add collapse to the equations. Others find it extravagant because it multiplies reality with every quantum event. The key point is that many worlds isn't an add-on to quantum mechanics. It's what you get when you take the Schrödinger equation seriously and apply it to everything without special exceptions. The branching emerges from following the math. This is the most extreme version, proposed by Max Tegmark. It suggests that every mathematically consistent structure exists physically, not just universes with different arrangements or different quantum branches or different constants. Universes with completely different mathematical structures underlying their physical laws. The idea starts with an observation. Physics describes the universe using mathematics. The deeper we look, the more we find that mathematical structures underlie everything. Particles are described by equations. Forces follow mathematical laws. Space and time can be represented as mathematical objects. Tegmark asks, is mathematics just a tool we invented to describe reality? Or is mathematics what reality actually is? If our universe is a mathematical structure, not just described by one, but actually identical to one, then why should only one mathematical structure exist physically? Mathematics doesn't play favorites. The number 7 is just as mathematically real as the number 3. A universe where space has 2 dimensions is just as valid mathematically as one with 3 dimensions. So why should one set of mathematical equations correspond to physical reality while others remain abstract? Tegmark's answer: they all exist. All mathematical structures are real universes. Ours is just one among infinitely many. There are universes where time has multiple dimensions. Universes where space is discrete rather than continuous. Universes based on mathematical structures so alien we can barely conceive of them. This is by far the least accepted multiverse proposal. Most physicists think it's crossed too far into philosophy, but it raises deep questions about the relationship between mathematics and reality that are interesting even if level 4 itself is wrong. Let's dig deeper into the concept that underlies level 1 and parts of level 2, infinity, and what it implies. Most of us have an intuitive grasp of infinity. It means going on forever. But infinity has counterintuitive properties that our everyday intuition doesn't prepare us for. Here's a simple example. There are infinite positive integers, 1, 2, 3, and so on forever. There are also infinite even numbers, 2, 4, 6, and so on forever. Which set is bigger? Your intuition might say the integers, because they include both odd and even numbers. But mathematically, the sets are the same size. Both are infinite. You can pair each integer with an even number and never run out of partners for either set. This is the first strange thing about infinity. An infinite set can be the same size as a proper subset of itself. This breaks our normal rules about counting. Now, apply this to the universe. If space is infinite, there are infinitely many regions the size of the observable universe. Call each region a Hubble volume. In each Hubble volume, there's a finite number of particles that can be arranged in a finite number of ways. That finite number is huge, but it's not infinite. Let's do some rough math. The observable universe contains roughly 10 to the power of 80 particles. Each particle has quantum states. Taking into account all the possible quantum states of all the particles, the number of distinguishable configurations in one Hubble volume is roughly 10 to the power of 10 to the power of 120. That number is so large it's hard to comprehend. If you tried to count that high, going through one configuration every Planck time, the smallest meaningful unit of time, it would take vastly longer than the current age of the universe, vastly longer than will exist before the last stars burn out and the cosmos goes dark. But it's still finite, and if there are infinitely many Hubble volumes, then even this incomprehensibly large number of configurations must repeat. Not might repeat, must repeat, and must repeat infinitely many times. This is why duplicate U's are mathematically inevitable in an infinite universe. Not because of anything special about you, because of how infinity and finite combinatorics interact. Think of it this way. Imagine you have a bag with 100 different colored balls. You draw one ball, note the color, put it back, and draw again. If you do this 1,000 times, you'll probably see some colors repeated. If you do it 1,000,000 times, you'll definitely see repetitions. If you do it infinitely, many times, you'll see every possible color infinitely often. The same logic applies to arrangements of particles. There are many possible arrangements, but not infinitely many. If you sample infinitely often, you get repetitions. In an infinite universe, nature is essentially sampling from the finite set of possible Hubble volume configurations infinitely often. Repetition is guaranteed. Does this mean duplicates actually exist? Only if the universe is actually infinite. We don't know if it is. But if it is, the duplicates follow mathematically. There's another layer to this involving quantum mechanics. Even in a single Hubble volume, quantum mechanics says particles don't have definite states until measured. The number of possible quantum states is larger than the number of possible classical configurations. When you include quantum possibilities, the number of distinct states in a Hubble volume goes up significantly. But it's still finite. And infinity is still bigger than any finite number, no matter how large. This is the deep strangeness of infinity applied to cosmology. It doesn't just mean the universe is big, it means that if certain mathematical structures describe reality, then repetition, including duplicate U's, becomes inevitable. If the multiverse is real in any of its forms, several deeply strange implications follow. These aren't just abstract mathematical curiosities. They're genuine puzzles about identity, consciousness, and the nature of existence. In a level 1 infinite universe, there are infinite copies of you. They're not just similar to you. Some of them are atom for atom identical, with exactly the same quantum states, exactly the same memories, exactly the same thoughts you're having right now. What does this mean for personal identity? Are they you, or are they separate people who happen to be identical to you? In our normal experience, identity is tied to continuity. You're the same person you were yesterday because there's a continuous thread of experience and memory connecting yesterday you to today you. But the duplicate you in another Hubble volume has no such connection to you. They have identical memories, but they didn't share the experiences those memories encode. Their past is separate from your past, even though the records are identical. Philosophers have debated personal identity for centuries. The multiverse adds a new wrinkle. If there are beings atom for atom identical to you, sharing your exact mental state at this moment, are they you? If they make different choices in the next minute, do they become different people? Or were they always different people despite the momentary identity? There's no consensus answer. It depends on what you think personal identity fundamentally. In many worlds, the identity problem gets even weirder. Every quantum measurement causes branching. Your body contains roughly 10 to the power of 28 atoms, all undergoing quantum interactions constantly. The universe is branching in response to quantum events in your brain right now. This means there's no single future you. There's a branching tree of future yous, all equally real, all diverging based on quantum outcomes. Most branches are nearly identical. Some differ significantly based on rare quantum events that trigger macroscopic consequences. When the universe branches, which future you is the real you? The answer seems to be all of them. There's no privileged branch. Future you is not one person, but an ensemble of people, all with equal claim to being the continuation of present you. This has led some people to speculate about quantum immortality. The idea goes like this. Suppose you're in a life-threatening situation with quantum uncertainty in the outcome. Maybe a quantum event in your body determines whether a disease kills you. In most branches, you die. But in some branches, against overwhelming odds, you survive. From an external perspective, you almost certainly die. But from your subjective perspective, your continuous stream of consciousness can only follow the branches where you survive. You can't experience the branches where you die because there's no you there to experience anything. So your subjective experience might always thread through the surviving branches, no matter how improbable. You'd perceive yourself as impossibly lucky, surviving situations that should have killed you because the branches where you died can't be experienced. This is highly speculative and controversial. Most physicists who accept many worlds think quantum immortality is confused. The measure of branches where you survive might approach zero, making continued survival exponentially unlikely from any reasonable perspective. But it's the kind of strange implication that emerges when you take quantum branching seriously. Here's one of the most troubling implications of certain multiverse scenarios. If the cosmos is eternal and infinite, random thermal fluctuations should occasionally produce conscious observers by pure chance. Think about it. In an infinite time and space, any configuration of particles that's possible will occur eventually through random fluctuation. That includes a human brain, complete with false memories and thoughts, spontaneously assembling, existing for a moment, then dispersing. These are called Boltzman brains, named after the physicist Ludwig Boltzmann, who worried about related issues in statistical mechanics. Here's the problem. Creating a fully functional universe with stars, planets, and evolution requires many improbable events happening in sequence. Creating just a single brain that thinks it's in such a universe requires only one very improbable event. Random fluctuations are vastly more likely to produce lone brains than entire consistent universes. In certain eternal multiverse scenarios, there should be far more Boltzmann brains than normal evolved observers. And if that's true, you should expect to be a Boltzmann brain rather than a real evolved person. Your memories of having parents, going to school, living a life could all be false, implanted in a brain that formed moments ago by random chance and will dissolve moments from now. This seems absurd. You have every reason to think you're a real person, not a random fluctuation. So the fact that we're not Boltzmann brains suggests something is wrong with multiverse models that predict them as dominant. Physicists take this seriously as a constraint on cosmological theories. If your theory predicts more Boltzmann brains than normal observers, it's probably wrong or incomplete. Various solutions have been proposed, but none is fully satisfying yet. In an infinite multiverse, everything that can happen does happen infinitely many times. This creates a problem for calculating probabilities. Normally, probability is straightforward. You flip a coin, there are two possible outcomes, heads and tails. Each has a 50% probability. You can test this by flipping many times and counting the frequencies. But in an infinite multiverse, there are infinitely many coin flips resulting in heads and infinitely many resulting in tails. How do you compare infinite sets to determine probability? You need some way to weigh or measure the sets, a mathematical procedure for saying one infinity is larger or more probable than another. The problem is, there's no unique way to do this. Different measures give different answers, and we have no physical principle to tell us which measure is correct. This is called the measure problem, and it's a serious technical issue for eternal inflation and other infinite multiverse scenarios. Until it's resolved, predictions from these theories remain ambiguous. Physicists have proposed various solutions. Maybe we should weight by volume, maybe by the number of observers, maybe by some quantum mechanical measure related to the wave function. Each approach gives different results, and we can't determine empirically which is right. Now we come to the hardest question about the multiverse. If other universes exist, how could we ever know? Science is supposed to be about testable predictions, experiments that could prove ideas right or wrong. But other universes, by definition, seem beyond our reach. This is the core of the debate about whether multiverse ideas are even scientific. Let's start with what we might be able to test, at least in principle. For level 1 infinite space, we can measure the curvature of the universe. If space curves back on itself like the surface of a sphere, it's finite, and level 1 doesn't exist. If space is flat or curves like a saddle, it could be infinite, and level 1 could be real. Current measurements from the cosmic microwave background show space is flat to within measurement error. This is consistent with infinity, but doesn't prove it. For level 2 bubble universes, there's a slim possibility of direct detection. If two bubbles collided in the distant past, the collision might have left a signature in the cosmic microwave background. Think of two soap bubbles touching. There would be a distinct circular pattern where they made contact. Physicists have searched for such collision signatures. They haven't found any convincing ones yet, but the search continues as our instruments improve and our analysis techniques get more sophisticated. A clear collision signature would be smoking gun evidence for bubble universes. There's also the possibility of testing through fine-tuning. If the multiverse explains why constants have life-friendly values, we can make statistical predictions. We should expect to find ourselves in a universe where constants are just barely suitable for life, not much more favorable than necessary. We can measure the constants precisely and see if they match this prediction. The cosmological constant seems to fit this pattern, but one example doesn't prove much. For level 3 many worlds, the situation is trickier. Individual branches can never be observed from another branch once they've separated. But the theory makes predictions about quantum interference patterns that depend on multiple branches existing before they separate. There are proposed experiments that might distinguish many worlds from collapse theories. These involve creating macroscopic quantum superpositions and looking for specific signatures. The experiments are extremely difficult technically, but not impossible in principle. Some physicists think we might be able to test quantum interpretations in the coming decades. For level 4 mathematical structures, testing seems hopeless. How could we ever detect a universe with completely different mathematical laws? By definition, we couldn't interact with it or observe it in any way. But here's the hard truth. For the most dramatic predictions of multiverse theories, other universes themselves, direct observation seems impossible in principle. Level 1 duplicates are so far away that light from them will never reach us. The expansion of space carries them away faster than light can travel. We're causally disconnected forever. Level 2 bubbles are separated by eternally inflating regions. You can't travel from one bubble to another because the space between them is expanding faster than light. Each bubble is its own island universe, completely isolated from all the others except in the rare case of collision. Level 3 branches separate at the quantum level and can't interact once they've decohered. The version of you in another branch is as unreachable as if they were in another universe entirely. Level 4 universes with different mathematical structures might not even share concepts like space or time with our universe. There's no possible bridge or communication channel, so we face a dilemma. The most dramatic and interesting prediction of multiverse theories is unobservable by definition. Does that make multiverse ideas unscientific? This question has sparked fierce debates in physics and philosophy of science. Karl Popper famously argued that for something to be scientific, it must be falsifiable. There must be some possible observation that could prove it wrong. If no observation could ever disprove your theory, it's not science. By this criterion, multiverse hypotheses seem to fail. If we can't observe other universes, how could we ever prove they don't exist? Any observation is compatible with the multiverse because you can always say that's what our universe happens to show, while other universes show other things. Defenders make several counter-arguments. First, they say we're not testing the multiverse directly. We're testing underlying theories like inflation and quantum mechanics that happen to predict a multiverse. If inflation is right, and it predicts eternal inflation and bubble universes, we should believe in those bubbles even if we can't observe them, just like we believe in quarks inside protons even though we can't observe individual quarks in isolation. Second, they argue that demanding direct observation is too strict. Lots of things in science are not directly observable. We can't observe what's inside black hole event horizons, but we believe matter exists there. We can't rerun the Big Bang, but we believe in cosmology. Historical sciences deal with unique past events that can't be repeated. Why should multiverse hypotheses face a higher bar? Third, some philosophers argue that confirmation is more important than falsification. A theory gains support when it successfully predicts things we can observe. If multiverse theories make successful predictions about observable phenomena, even if we can't observe the multiverse itself, that should count as evidence. Critics respond that this reasoning is too loose. It allows too much speculation. If you can invoke unobservable entities to explain anything, you can make up whatever you want. The multiverse risks becoming a just so story, an explanation that can't be wrong because it's flexible enough to accommodate any observation. The debate continues. There's no consensus in the physics community about whether multiverse ideas cross the line from science into metaphysics. Personally, I think we need to be honest about the limits of current knowledge. The multiverse is not established science like atoms or DNA or the expansion of the universe. Those are backed by overwhelming direct evidence. The multiverse is speculative, emerging from theories that have other successful predictions but making claims we can't directly verify. That doesn't mean it's worthless. It means it's at the frontier, in that uncertain territory where science blends with philosophy. We should hold multiverse ideas tentatively as serious possibilities worth exploring, while remaining open to alternatives we haven't thought of yet. The history of science has examples both ways. Sometimes ideas that seemed untestable became testable with new technology. Continental drift seemed beyond proof, until seafloor spreading was discovered. Sometimes ideas that seemed promising turned out to be dead ends. The ether seemed necessary until Einstein showed light doesn't need a medium. We won't know which category the multiverse falls into until we have more information. Maybe new observations will provide indirect evidence. Maybe new theoretical insights will show it's inevitable. Maybe someone will find a better explanation that doesn't require other universes at all. For now, the honest answer is, we don't know. Let's shift from the science to the implications. Suppose some version of the multiverse turns out to be real. What would that mean for our understanding of our place in existence? For most of human history, we thought we were special. Earth was the center of the universe. Humans were unique creations. Our planet was the stage for the cosmic drama. Then came Copernicus. Earth isn't the center, it orbits the sun like other planets. Okay, we adjusted. Maybe the sun is special. Nope. The sun is one star among hundreds of billions in our galaxy. Well, maybe our galaxy is special. Nope again. Our galaxy is one among hundreds of billions in the observable universe. We're not central. We're not unique. We're cosmically insignificant. This is sometimes called the Copernican principle. We shouldn't assume we occupy a privileged position. Our location in the universe isn't special. The physics we observe should be typical. The multiverse would be the ultimate extension of this principle. Not only is our location in the universe not special, but our entire universe might not be special. It's one bubble among infinitely many, one branch among countless others, one solution in a vast landscape of possibilities. Our cosmic insignificance would reach a new level. We'd be an infinitesimal part not just of the universe, but of the multiverse. Some people find this depressing. If we're that insignificant, does anything matter? But you could flip it around. If the multiverse exists, it means reality is far richer and more complex than we imagined. Existence isn't limited to what we can see. There's vastly more out there, forever beyond our reach, but nonetheless real. And locally, nothing changes. We still experience this universe, this timeline, this quantum branch. Whatever else exists, this is where we are. Our choices still determine the life we experience. Our actions still have consequences in the reality we inhabit. The existence of other universes doesn't diminish the significance of this one any more than the existence of other galaxies diminishes Earth. You still live your one life. What happens to you still matters to you. In fact, the multiverse might make existence seem more precious. Out of all the possible universes, we happen to be in one where the constants allow for stars, planets, chemistry, complexity, consciousness, and life. That's remarkable. Whether it's unique or one of many, it's still special to us. There's also a philosophical angle worth considering. The multiverse offers a naturalistic explanation for fine-tuning without requiring design. The constants aren't tuned because someone set them. They vary across universes, and we necessarily observe values compatible with our existence. It's a selection effect, not evidence of purpose. This doesn't prove anything about larger questions of meaning or purpose. You can believe in the multiverse and still find meaning in your life. You can reject the multiverse and still be a naturalist. The multiverse is about physics and cosmology, not about values or purpose. But it does shift how we think about our relationship to the cosmos. We're not central, we're not the point, we're observers in one particular region of a reality that might be far vaster than we ever imagined. To me, that's humbling in a good way. It reminds us not to be too certain, not to assume we have everything figured out. Reality keeps turning out to be stranger than we expected. The multiverse, if real, would be another step in that long history of discovering that existence is bigger and weirder than our ancestors imagined. So where does actual scientific work stand on the multiverse? What are researchers actually doing? It's not like there are multiverse detectors being built. The work is mostly theoretical, but that doesn't mean it's not rigorous or valuable. Physicists working on inflation are refining models to understand which versions lead to eternal inflation and which don't. They're calculating the properties of bubble universes and working on the measure problem, trying to find a natural way to assign probabilities in an infinite multiverse. Groups at institutions like Stanford, MIT, and Cambridge run computer simulations of inflationary scenarios. They're exploring whether eternal inflation is inevitable given certain field configurations. In quantum mechanics, researchers are testing interpretations by pushing quantum behavior to larger and larger scales. Labs have created superpositions of molecules containing thousands of atoms. They're working toward demonstrating quantum effects with macroscopic objects like tiny mirrors and mechanical oscillators. Every time we extend quantum behavior to larger scales, we learn something about where the quantum to classical transition happens. There are proposals for experiments that might distinguish many worlds from collapse theories. These involve measuring quantum systems in ways that would show different statistical patterns depending on whether branching occurs. The experiments are extremely difficult, but potentially doable with future technology. String theorists are exploring the landscape, trying to understand which configurations are stable. Some focus on swampland conjectures, which aim to identify configurations that can't be consistently formulated, potentially reducing the landscape. Others work on mathematical connections between string theory, geometry, and number theory. Even if string theory doesn't describe our universe, these mathematical insights have value. Cosmologists are analyzing data from satellites and telescopes for signatures that might reveal early universe physics. They're measuring fundamental constants more precisely to test anthropic predictions. Upcoming gravitational wave observatories might provide new ways to probe the early universe and test inflation. Philosophers are working on conceptual foundations. What does probability mean across parallel realities? What does testability require? When is anthropic reasoning legitimate? How should we think about personal identity in many worlds? These aren't idle speculations, but rigorous analyses using tools from philosophy of science, probability theory, and decision theory. All of this is real work, even if it doesn't directly prove or disprove the multiverse. And here's something important. Even if the multiverse turns out to be wrong, this work isn't wasted. Understanding inflation better helps us understand the early universe regardless of whether it's eternal. Clarifying quantum foundations is valuable regardless of which interpretation is correct. Mathematical insights from string theory can inform other areas of physics. Science often works this way. You pursue an idea, develop tools and frameworks along the way, and even if the original idea fails, the tools remain valuable. The multiverse might be one of those ideas that's wrong but productive, or it might turn out to be right. We honestly don't know yet. Now that we've outlined the 4 levels, let's dig deeper into the actual physics that might make each one possible. This isn't just philosophical speculation. These ideas rest on real equations, real observations, and real theoretical frameworks that physicists work with every day. Level 1 multiverse depends on a simple question: does space go on forever? This might seem like something we could never know, but we can actually constrain it through measurement. Space can have different geometric properties. It can be flat like an infinite sheet of paper. It can curve positively like the surface of a sphere, which would make it finite with no edge. Or it can curve negatively like a saddle, which also allows for infinite extent. General relativity tells us that matter and energy curve space. The density of matter in the universe determines its overall curvature. If the density is exactly at a critical value, space is flat. If it's higher, space curves positively and is finite. If it's lower, space curves negatively. We can measure this density by looking at the cosmic microwave background radiation. The pattern of hot and cold spots in this radiation depends on the curvature of space. Specifically, the angular size of typical fluctuations tells us about geometry. Satellites like WMAP and Planck have measured this with extraordinary precision. The result? Space is flat to within about 0.5% margin of error. This is consistent with infinite extent, though it doesn't prove it. Space could still curve so gently that our measurements can't detect it yet. But here's the thing. Inflation actually predicts flat space. During inflation, any initial curvature gets stretched to nearly zero, the way wrinkles in a balloon disappear when you inflate it. So the observation that space is flat supports inflation. And inflation naturally leads to a universe that's either infinite or so large it might as well be. If space is infinite and the laws of physics are the same everywhere, level 1 multiverse follows mathematically. The finite number of possible particle arrangements in any volume must repeat across infinite volumes. There's no way around it. Level 2 comes from taking inflation seriously as a quantum field theory. Let's unpack what that means. Inflation is driven by a field called the inflaton. Think of it like an energy field permeating all of space. When the inflaton field has high energy, it creates a negative pressure that makes space expand exponentially fast. When the field settles to lower energy, inflation stops. But this field is also subject to quantum mechanics. At the quantum level, fields fluctuate randomly. In most regions, these fluctuations average out. But occasionally, a quantum fluctuation can push the inflaton field from high energy to low energy in some localized region. When that happens, inflation stops in that region, creating a bubble universe. But here's the key. While this bubble is forming, the space outside it is still inflating. And inflation is so rapid that even though bubbles are constantly forming, the total volume of inflating space actually increases over time. Imagine a block of Swiss cheese. You're drilling new holes constantly, but the block is expanding so fast that despite the holes, there's more cheese than there was before. That's roughly what's happening with eternal inflation. Bubble universes form, but the inflating space between them grows faster than bubbles can fill it. This means inflation, once started, never completely ends. It continues creating new bubble universes forever. Our observable universe is the interior of one such bubble. There are countless others, forever beyond our reach. Now, when each bubble forms, the inflaton field settles into its low-energy state. But quantum field theory says there can be multiple low-energy states, like multiple valleys in an energy landscape. Different bubbles might settle into different valleys, giving them different physics. This is where string theory comes in. String theory is an attempt to unify all forces and particles by treating them as vibrations of tiny strings. For the math to work, string theory requires extra spatial dimensions beyond the three we experience. These extra dimensions must be curled up very small. But there are many ways to curl up these dimensions. The number might be as large as 10 to the power of 500. Each way of curling them up gives different physics, different particle masses, different force strengths, different constants. If eternal inflation is real, and string theory is correct, different bubble universes might sample different ways of curling up the extra dimensions. Each bubble would have its own physics, its own constants, its own laws. Most bubbles would be lifeless. The vast majority of ways to set the constants result in universes where stars don't form, atoms are unstable, or chemistry doesn't work. But among infinite bubbles, some would have constants that allow complexity and life. We find ourselves in such a bubble not because we're special, but because we couldn't exist in the lifeless ones to observe them. It's a selection effect across the landscape of possible physics. Is this right? We don't know. Inflation has strong observational support. Whether it's eternal is less certain. String theory remains unproven. The landscape might be an artifact of not fully understanding the theory, but if the basic ideas are correct, eternal inflation and level 2 multiverse would seem to follow. Level 3 requires understanding what quantum mechanics actually says and why it's so strange. The fundamental equation of quantum mechanics is the Schrödinger equation. It describes how quantum states evolve over time. And here's the remarkable thing. The Schrödinger equation is completely deterministic. Given the current quantum state, you can predict exactly what the state will be at any future time. But there's a problem. When you measure a quantum system, you don't get the predicted quantum state. You get one definite classical outcome. An electron that was in a superposition of spinning clockwise and counterclockwise becomes definitely one or the other when you measure it. The traditional Copenhagen interpretation says this is wave function collapse. Measurement causes the superposition to collapse into one outcome, with probabilities determined by the quantum state. But the Schrödinger equation doesn't include collapse. It's something added on top, a separate rule that applies when measurement happens. This raises immediate questions. What counts as measurement? Where's the boundary between quantum and classical? Does consciousness play a role? These questions plagued quantum mechanics from the beginning. Hugh Everett proposed a radically simple solution. Don't add collapse. Just apply the Schrödinger equation to everything, including measuring devices and observers. Follow the math wherever it leads. When you do this, something interesting happens. The quantum state of the combined system, particle plus measuring device plus environment, evolves into a superposition of branches. One branch has the particles spinning clockwise, and the device registering clockwise and you seeing clockwise. Another branch has counterclockwise for all three. Both branches are real. Both exist in the quantum state. They've separated through a process called decoherence, which makes them unable to interfere with each other. From inside any branch, you see one definite outcome. But from a God's eye view outside the quantum state, all outcomes happen. This is many worlds. It's not an addition to quantum mechanics. It's what you get by taking the Schrödinger equation seriously and not adding special collapse rules. Does this interpretation make sense? Physicists argue about it. Some find it elegant because it's more minimal. One equation, no exceptions. Others find it extravagant because it multiplies reality at every quantum event. But many worlds does make a testable prediction. Quantum interference experiments depend on multiple paths or states existing and interfering with each other. Many worlds says these are real branches that later merge back. Collapse theories say only one outcome was ever real. Careful experiments might be able to distinguish these scenarios. Level 4 is the most philosophically radical. It claims that mathematics and physical reality are the same thing. This idea starts with an observation about how physics works. Every successful physical theory is fundamentally mathematical. Newtonian mechanics, differential equations describing forces and motion. Electromagnetism, Maxwell's equations governing electric and magnetic fields. Quantum mechanics, wave functions evolving according to the Schrödinger equation. General relativity, curved spacetime described by Einstein's field equations. The more precisely we understand physics, the more mathematical it becomes. At the deepest level we've reached, there's nothing but mathematical structure. Particles are representations of symmetry groups. Forces come from gauge fields. Space and time are geometric objects. Everything reduces to mathematics. So Tegmark asks, what if there's no distinction? What if the universe doesn't just have mathematical structure, but is mathematical structure? Not described by mathematics, but made of it, identical with it. If that's true, then asking why our particular mathematical structure exists while others don't is like asking why the number 7 exists while the number 3 doesn't. All mathematical structures exist in the same sense. The number 7 doesn't need a creator or a physical instantiation. It just is, as a matter of mathematical truth. By the same logic, all mathematically consistent structures that could describe a physical universe would exist as physical universes. They're not abstract constructs. They're real, just as real as ours, existing in exactly the same way mathematics exists. This leads to level 4 multiverse. All possible mathematical structures realized as physical realities. Universes with different numbers of dimensions, different symmetries, different fundamental entities. Universes so alien that concepts like particles or fields or cause and effect might not apply. This is speculative in the extreme. Most physicists think it's gone beyond physics into pure philosophy. But it does raise a genuine, deep question. Why is mathematics so unreasonably effective at describing reality? Why does the universe obey mathematical laws at all? One possible answer, because it is mathematical laws, not described by them, but identical to them. And if that's true, then other mathematical structures have equal claim to physical existence. Let's explore what the multiverse would mean for some of the biggest questions we can ask. One of the most striking features of our universe is how precisely calibrated it seems to be for life. Change certain fundamental constants by tiny amounts and the universe becomes sterile. Consider gravity. If it was stronger by about 1 part in 10 to the power of 40, stars would burn out in millions of years instead of billions, too fast for life to evolve. Make it weaker, and stars wouldn't ignite at all. The range for life-supporting gravity is incredibly narrow. The electromagnetic force has similar fine-tuning. Slightly stronger, and electrons wouldn't bond properly. Slightly weaker, and chemistry doesn't work. The mass difference between protons and neutrons is critical. Change it, and atomic nuclei become unstable. The cosmological constant is perhaps the most extreme example. This is the energy density of empty space itself. Quantum field theory predicts it should be enormous, about 10 to the power of 120 times larger than what we observe. But it's actually tiny. Just large enough to cause the universe to accelerate its expansion, but not so large that galaxies couldn't form. Why? In a single unique universe, this is baffling. You need either incredible luck, some unknown principle that forces these values, or deliberate design. The multiverse offers another explanation. If there are many universes with different constants, we necessarily find ourselves in one where the constants allow life, not because ours is special, but because we couldn't exist in the others. This is called anthropic reasoning, and it's controversial. Critics say it's giving up on finding real explanations. Defenders say it's the best explanation we have given what the math tells us. Steven Weinberg made an anthropic prediction about the cosmological constant in 1987. He calculated that if it varies across a multiverse, observers should find values small enough to allow galaxy formation, but not much smaller. When we measured it in 1998, the value was in his predicted range. This doesn't prove the multiverse exists, but it shows anthropic reasoning can make predictions that match observations. That's more than philosophical hand-waving. If the multiverse is real, it creates profound problems for how we think about probability. In normal probability theory, you have a sample space of possible outcomes and a measure assigning weights to different outcomes. You flip a coin, 2 outcomes, equal weights, 50% probability each. But in an infinite multiverse, there are infinite outcomes of every type. Infinite coin flips landing heads, infinite landing tails. How do you calculate probabilities from infinite sets? You need a measure, a way of weighting different regions of the multiverse. But there's no unique natural measure. Different choices give different predictions. For example, should we weight by spatial volume, by number of observers, by some quantum mechanical amplitude? Each gives different answers about what we should expect to observe. This is the measure problem, and it's a serious obstacle for multiverse theories. Without a solution, predictions remain ambiguous. We can't calculate probabilities precisely. Physicists have proposed various approaches. Maybe the measure should be based on the quantum wave function. Maybe on the distribution of matter. Maybe on some principle we haven't discovered yet. But no proposal has achieved consensus. Until this is solved, eternal inflation and other infinite multiverse scenarios can't make precise quantitative predictions. They can say certain things should be typical and others rare, but exact probabilities remain undefined. If you have duplicates in other regions of space or other quantum branches, what does that mean for personal identity? In philosophy, personal identity typically depends on continuity. You're the same person you were yesterday because there's a continuous thread of experience and causality connecting past you to present you. But your duplicate 10 to the power of 10 to the power of 29 meters away has no such connection to you. They have identical memories, but those memories encode experiences that happened to them, not you. Your histories are separate, even though the records are identical. Are they you? Most philosophers would say no. They're a different person who happens to be identical to you at this moment. If they make different choices in the next minute, they diverge, but they were separate people all along. Quantum branching is even stranger. When the universe splits, both future versions have equal claim to being the continuation of present you. There's no fact of the matter about which one is really you. Both are. This challenges the notion that you have a single future. Instead, you have a branching tree of futures, all equally real. Your future isn't one person, but an ensemble of people, all descended from present you through quantum branching. Some people find this troubling. Others find it liberating. Every path gets explored. Every possible version of your life gets lived somewhere in the branching structure of reality. But it does force us to rethink what identity means in fundamental ways. Does the multiverse make life meaningless? If every choice you make gets made differently in other branches, and all outcomes are equally real, why should any particular choice matter? This is a common worry, but I think it's confused. Even in a multiverse, your choices determine which branch you experience. The version of you that makes good choices lives in a better branch. The version that makes bad choices lives in a worse one. Those outcomes matter to the people experiencing them, even if all versions exist. Pain is still painful, joy is still joyful, suffering still matters, success still feels good. Think of it this way. Right now, somewhere on Earth, someone is experiencing terrible suffering while someone else experiences happiness. Both are real. The existence of happiness elsewhere doesn't make suffering less bad. The existence of suffering elsewhere doesn't make happiness less good. The same logic applies across the multiverse. The fact that other versions exist doesn't diminish what happens to you. Your life still matters to you. Your choices still shape your experience. If anything, the multiverse might make existence more precious. Out of all possible realities, you happen to be in one that allows for consciousness, complexity, and life. That's remarkable, whether it's unique or one of many. The multiverse doesn't answer questions about meaning or purpose. Those are separate from questions about cosmology. You can believe in the multiverse and find meaning in your life. You can reject the multiverse and still be a naturalist. Physics tells us what exists. It doesn't tell us what matters or how to live. Those are separate domains of inquiry. We've explored why physicists consider the multiverse and what it would mean if true. But it's important to present the skeptical case as well. Many physicists think multiverse ideas have gone too far. The core objection is that multiverse hypotheses are unfalsifiable. Other universes can't be observed by definition. So how could we ever prove the idea wrong? Science is supposed to work through testable predictions. You propose a theory, derive predictions, do experiments. If predictions match observations, the theory gains support. If not, it's falsified. But multiverse theories seem to escape this cycle. You can't do experiments on other universes. You can't travel to them or detect them directly. So the central claim is beyond empirical test. Defenders respond that we're testing underlying theories that happen to predict multiverses. We can test inflation through cosmic microwave background observations. We can test quantum mechanics through interference experiments. If these theories are right, and they predict multiverses, we should believe the prediction. But critics say this is too indirect. Just because a theory is successful in its testable domain doesn't mean all its predictions are true. Maybe inflation is approximately right, but eternal inflation is wrong. Maybe quantum mechanics is correct, but many worlds is not the right interpretation. Without direct tests of the multiverse itself, how can we be confident? Historically, when theories encounter problems, scientists sometimes add epicycles, extra entities or mechanisms to save the theory. The most famous example is the epicycles added to geocentric astronomy. As observations improved, Earth-centered models needed more and more complications to match the data. Eventually, the Sun-centered model replaced them because it was simpler. Is the multiverse another epicycle? Are physicists adding infinite, invisible universes to save theories that don't quite work? The historical parallel is the ether. 19th century physicists thought light needed a medium to propagate through, so they proposed an invisible substance called the ether filling all of space. The ether had to have increasingly strange properties to match observations. Ultimately, Einstein showed light doesn't need a medium. The ether was unnecessary. Maybe the multiverse is our generation's ether. Maybe in decades, someone will find a better approach that explains fine-tuning and solves the measurement problem without requiring other universes. Defenders note a key difference. The ether was proposed specifically to fill a perceived need. The multiverse wasn't. It emerged from theories developed for other reasons. Inflation explains features of the cosmic microwave background. Quantum mechanics describes atomic behavior. String theory attempts to unify forces. The multiverse is a byproduct, not the goal. That makes it harder to dismiss as an epicycle. Physicists weren't trying to invent extra universes. They were solving other problems, and extra universes kept appearing in the math. Still, the historical warning is worth taking seriously. Ideas that seem necessary sometimes turn out to be wrong. Some critics argue that the measure problem isn't just a technical difficulty, but a fatal flaw. If you can't define probabilities in an infinite multiverse, the theory can't make predictions. And if it can't make predictions, it's not science. This is a strong objection. Predictions are the heart of scientific theories. Without them, you have mathematical speculation, not physics. Defenders argue that progress is being made on the measure problem. Various proposals exist, and while none is fully satisfactory, they're getting better. Maybe a breakthrough is coming. Critics respond that decades of work haven't solved it, suggesting the problem might be fundamental rather than technical. Maybe infinite multiverses are inherently unpredictable. Some physicists reject the multiverse on grounds of simplicity. Occam's razor says we should prefer simpler explanations. One universe is simpler than infinite universes. Defenders counter that Occam's razor is about simplicity of assumptions, not simplicity of ontology. Many worlds has simpler assumptions than Copenhagen interpretation. Just the Schrödinger equation, no collapse. Eternal inflation is simpler than inflation that somehow stops everywhere simultaneously. The theories are simple. The predicted reality is complex. But science has always valued simple laws that generate complex phenomena. Critics say this is playing word games. When people talk about simplicity in science, they mean preferring theories that don't multiply entities unnecessarily. Infinite universes seem like unnecessary multiplication. The debate continues without clear resolution. Many physicists are uncomfortable with anthropic reasoning. It feels like giving up on finding real explanations. For decades, physics advanced by discovering principles that explain why things are the way they are. The mass of the proton seemed arbitrary until we understood it emerges from quark dynamics. Force strengths seemed unrelated until unification theories connected them. Anthropic explanations end this search. Instead of explaining why the cosmological constant is tiny, you say it varies, and we observe a small value because we couldn't exist otherwise. That's not an explanation in the traditional sense. It's a selection effect. Maybe real explanations exist that we haven't found yet. Maybe some unknown principle forces the constants to their observed values. Jumping to anthropic reasoning might stop us from looking. Defenders argue that anthropic reasoning should be a last resort, used only after exhausting other possibilities. And they note that some problems might genuinely have anthropic solutions. Not everything needs a deeper explanation. But the worry remains that multiverse thinking could discourage the search for fundamental principles that really do explain why constants have their values. Despite the controversies, serious work continues on multiverse-related topics. Let's look at what's actually happening in research. The foundation of Level 2 multiverse is inflation, and inflation is testable. We can look for signatures in the cosmic microwave background radiation. Inflation predicts specific patterns in the temperature fluctuations of the CMB. The observed patterns match predictions remarkably well. This is why inflation has become mainstream cosmology. We can also search for gravitational waves from inflation. These would appear as a particular polarization pattern in the CMB called B modes. The BICEP 2 experiment thought they found this in 2014, but it turned out to be dust in our galaxy. The search continues with better instruments. If we detect primordial gravitational waves, it would be strong evidence for inflation. It wouldn't prove eternal inflation, but it would validate the underlying theory. We can also search for bubble collisions. If our bubble universe collided with another in the distant past, it might have left a circular pattern in the CMB. Several groups have searched for such signatures. None have been convincingly detected, but the search continues. For Level 3 many-worlds, experiments are pushing quantum behavior to larger scales. Researchers have created superpositions of increasingly large molecules. The current record is molecules with over 2,000 atoms. There are proposals to put viruses and eventually microscopic mirrors into superposition states. Every time we extend quantum behavior to larger scales, we test the boundaries of quantum mechanics. We might find that superposition breaks down at some scale, which would constrain interpretations. There are also proposed tests that might distinguish collapse from no-collapse theories. These involve measuring quantum systems in specific ways and looking for statistical signatures that differ between interpretations. The experiments are difficult, but progress is being made. Within decades, we might have empirical evidence favoring one interpretation over others. For the landscape and Level 2 multiverse, string theorists are working to understand which configurations are actually stable. The Swampland program aims to identify which apparent string theory solutions are inconsistent. If successful, it might dramatically reduce the landscape, potentially making string theory more predictive. There's also work on connecting string theory to observable physics. If string theory predicts specific signatures we could detect, that would make it more testable even if we can't observe other universes directly. Philosophers are clarifying conceptual issues around the multiverse. What does probability mean in an infinite multiverse? Various proposals exist using different mathematical frameworks. Some use limits of finite regions. Others use decision theory rather than frequentist probability. When is anthropic reasoning legitimate? Philosophers are developing criteria for distinguishing valid anthropic arguments from invalid ones. How should we think about confirmation for theories that make untestable predictions? This connects to broader questions in philosophy of science about what makes theories scientific. This philosophical work matters because it helps us think clearly about what multiverse theories actually claim and what would count as evidence for or against them. After exploring the multiverse for 2 hours, what should we conclude? The honest answer is, we don't know if it's real. The evidence is indirect and controversial. The testable predictions are limited. The philosophical objections are serious. But we also shouldn't dismiss it as mere speculation. It emerges from our best attempts to understand real phenomena. Multiple independent lines of inquiry point toward it. Serious physicists take it seriously for good reasons. This puts us in an uncomfortable position. The multiverse might be one of the greatest discoveries in human history. Or it might be a wrong turn that seemed plausible given our current knowledge but will be abandoned when we understand better. How should we think about ideas in this uncertain space? First, we should hold them tentatively. The multiverse is a hypothesis, not established fact. We should be ready to abandon it if better explanations emerge or if crucial flaws are found. Second, we should pursue it rigorously. If the idea has merit, we'll discover it through careful investigation. If it's wrong, we'll find that out too. But only by engaging seriously with the hypothesis can we make progress. Third, we should maintain epistemic humility. We don't know what we don't know. Reality has surprised us before. Our current theories might be missing something crucial. The answer might be something we haven't imagined yet. Fourth, we should remember that even wrong ideas can be productive. The search for the luminiferous ether led to special relativity. The puzzle of black-body radiation led to quantum mechanics. Sometimes pursuing wrong ideas with the right methods yields unexpected insights. The multiverse might be like that. Even if it's wrong, working through its implications teaches us about quantum mechanics, cosmology, probability theory, and the nature of scientific explanation. Or it might be right. Maybe reality really is vastly larger than we imagined. Maybe existence extends far beyond what we can observe. Maybe we're one small part of an infinite cosmic ensemble. Either way, engaging with the question pushes our understanding forward. What does this mean for how we should live? Probably nothing. The multiverse, if real, doesn't change the fact that you're here, experiencing this universe, living this life. Your choices still determine your experience. Your actions still matter to you. The existence of other universes, or other quantum branches, doesn't make your life less meaningful any more than the existence of other people makes your life less meaningful. You're still you, living your singular subjective experience, even if infinitely many other versions exist elsewhere. If anything, the multiverse might make existence seem more remarkable. The fact that we're here, conscious, able to ask questions about the deepest nature of reality, is extraordinary. Whether we're alone or surrounded by infinite other universes, that fact remains. The universe we experience allows for stars, planets, chemistry, complexity, consciousness, and life. Whether that's a unique occurrence or one instance of infinite variations, it's still astounding. So here we are. We've explored the multiverse hypothesis from every angle. We've looked at the physics, the philosophy, the implications, the objections. We've seen why some of the brightest minds in science take it seriously and why others remain skeptical. The journey has taken us from the mathematics of infinity to the nature of consciousness, from cosmic inflation to quantum branching, from fine-tuned constants to the meaning of existence. And we've arrived at uncertainty. Not the comfortable certainty of established science, but the productive uncertainty of the frontier where knowledge meets mystery. That's where we are with the multiverse. At the edge of what we know, looking out into what we might discover. The questions are profound, the stakes are high, the answers remain elusive. But that's what makes this journey worthwhile. Not the destination, but the exploration itself. The willingness to ask the hardest questions, even when answers are uncertain. The courage to follow logic wherever it leads. The honesty to admit when we don't know. That's the scientific spirit. That's what moves humanity forward. Not claiming knowledge we don't have, but pursuing understanding wherever it takes us. The multiverse might be real. It might not. We might discover the truth in our lifetime. We might never know for certain, but we can wonder. We can reason. We can calculate. We can observe. We can theorize. We can test what's testable and think carefully about what's not. And in that pursuit, in that endless human drive to understand the cosmos we inhabit, we find something profound. Not certainty, but meaning. Not answers, but better questions. Not the end of mystery, but deeper engagement with it. The multiverse breaks our reality in the sense that it shatters our assumptions about what might exist. It challenges us to expand our conception of possible existence beyond anything our ancestors imagined. But reality itself doesn't break. It simply is, whatever it is. Our theories are models, approximations, attempts to understand something vastly larger than ourselves. What's changing is our understanding, our willingness to consider ideas that seem absurd, our ability to follow mathematics into strange territory, our courage to ask questions that might not have answers. That willingness, that ability, that courage is what makes us human. We're pattern-seeking, meaning-making, wondering creatures, blessed and cursed with consciousness that allows us to ask why. The multiverse gives us plenty to wonder about. Infinite copies of ourselves in distant regions of space. Bubble universes with different physics. Quantum branches splitting at every moment. Mathematical structures realized as physical realities. Whether any of it is true, the fact that we can conceive it and reason about it and take it seriously as a scientific hypothesis shows how far human thought can reach. And that's beautiful. That's worth celebrating. Not the multiverse itself, which might or might not exist, but our capacity to imagine it, to work out its implications, to develop tests for what can be tested, and to think carefully about what can't. We are finite beings contemplating infinite possibilities. Temporary patterns of matter asking eternal questions. Brief sparks of consciousness illuminating vast darkness. The multiverse, real or not, is part of that illumination. Part of our endless reach beyond ourselves. Part of what makes us human. And in the end, maybe that's enough. Maybe the journey of understanding is its own reward. Maybe the questions matter more than the answers. Maybe wonder itself is what we're really after. The cosmos doesn't owe us answers. Reality is under no obligation to be comprehensible to evolved apes on one small planet in one universe among possibly infinite others. But we ask anyway. We wonder anyway. We reach anyway. And in that reaching, we find what it means to be human. The multiverse awaits. Real or imaginary, proven or disproven, it represents the furthest frontier of human thought about the nature of existence. Whether you believe it or doubt it, whether you find it inspiring or unsettling, it's a window into how deeply we can think and how far we can wonder. And that window, that capacity for deep thought and far wondering, might be the most remarkable thing of all. Beyond the physics and mathematics, the multiverse forces us to confront profound questions that touch on philosophy, consciousness, and the nature of reality itself. One of the deepest mysteries in science is why mathematics describes the physical world so effectively. Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Think about it. Mathematics is a human invention, developed through pure logic and abstract reasoning. We didn't design it to describe reality. We developed it to solve puzzles, to understand patterns, to explore logical structures. Yet when we look at nature, we find it follows mathematical laws with extraordinary precision. Planets orbit according to mathematical equations. Light propagates following mathematical principles. Particles behave exactly as mathematical theories predict. This is strange. Why should the universe care about human mathematical constructs? Why should our abstract logical games correspond so precisely to physical reality? One answer is that mathematics isn't our invention, but our discovery. Mathematical truths exist independently of us, and physics is simply the study of which mathematical structures describe our universe. If this is right, then Tegmark's Level 4 multiverse becomes more plausible. If mathematics exists independently, and physical reality is fundamentally mathematical, then all mathematical structures might be equally real as physical universes. This doesn't prove Level 4, but it suggests the question isn't absurd. The relationship between mathematics and physics is genuinely mysterious, and the multiverse might be part of the answer. The multiverse also forces us to think carefully about existence itself. What does it mean for something to exist? In everyday language, exist means being part of the physical world we can interact with. This chair exists because you can sit on it. That star exists because telescopes can detect its light. But quantum mechanics already challenges this simple picture. Do superposition states exist before measurement? They're real in the mathematics. They affect experimental outcomes, but they can't be directly observed. The multiverse takes this further. Other universes, other quantum branches, other regions of infinite space might be real in the sense that they're part of the complete mathematical description of reality. But they can't interact with us or be observed. Do they exist? The question forces us to refine what we mean by existence. Maybe there are degrees of existence. Maybe something can be real without being observable. Maybe existence is a broader concept than we thought. Philosophers distinguish between physical existence and mathematical existence. Numbers exist mathematically. Chairs exist physically. The multiverse blurs this distinction. Other universes might be as physically real as ours, but as observationally inaccessible as mathematical abstractions. This isn't just word games. It's a genuine conceptual puzzle about what we mean when we say something is real. The multiverse raises another unsettling possibility. In an infinite multiverse with infinite technological civilizations, some will develop the capability to run detailed simulations of universes. If creating simulated universes is possible, and if infinitely many civilizations eventually do it, then there would be vastly more simulated universes than base-level real ones. By pure probability, we'd be more likely to be in a simulation than in base reality. This is the simulation argument made famous by philosopher Nick Bostrom. It doesn't prove we're in a simulation, but it suggests one of three things must be true. Advanced civilizations never develop simulation capabilities, they choose not to run simulations, or we're probably in a simulation. The multiverse amplifies this argument. With infinite universes, infinite simulations become almost inevitable. The ratio of simulated to real universes approaches infinity. Does this matter? Maybe not practically. If the simulation is detailed enough, it makes no difference to your experience whether it's real or simulated. You exist either way. Your experiences are real to you either way. But it's another example of how multiverse thinking challenges our basic assumptions about reality. Let's look at a specific example of fine-tuning that the multiverse might explain: the fine structure constant. This number, approximately 1/137, determines the strength of electromagnetic interactions. It's dimensionless, meaning it's a pure number, not dependent on what units you use. Why is it 1/137? Nobody knows. You can't calculate it from deeper principles in current theory. You measure it and plug it in. But this value is critical. If it was slightly different, chemistry wouldn't work properly. Carbon wouldn't form the right bonds. Water wouldn't have the right properties. Life, as we know it, would be impossible. In a single universe, this seems like an incredible coincidence. The fine structure, constant, could have been any value, but it happens to be in the narrow range that allows complex chemistry. In a multiverse where this constant varies, the mystery dissolves. We observe a life-friendly value because we couldn't exist in universes with life-hostile values. It's anthropic selection, not coincidence. Does this explanation feel satisfying? To some physicists, yes. It explains why we observe what we observe without requiring improbable luck or fine-tuning. To others, it feels like giving up. They'd prefer to find a deeper principle that forces the fine structure constant to its observed value. The debate reflects different views about what counts as explanation in physics. The multiverse might also shed light on why time has a direction. Why does entropy increase? Why do we remember the past but not the future? Why does time flow forward? The standard answer involves the Big Bang. The universe started in a low entropy state. Entropy has been increasing ever since. We remember the past because brains encode information about low entropy states, and those only exist in the past direction from our current state. But this just pushes the question back. Why did the universe start with low entropy? What explains the special initial conditions? In an infinite multiverse with eternal inflation, different regions might have different entropy histories. Most regions would be in thermal equilibrium, high entropy, lifeless. But occasionally, random fluctuations create low entropy pockets that then evolve toward higher entropy. We necessarily find ourselves in such a pocket because only low entropy regions evolving toward higher entropy allow for life and observers. This might explain the arrow of time without requiring special initial conditions. The conditions aren't special. They're just anthropically selected from a vast ensemble. Again, some find this satisfying. Others think it's an evasion of the real question. Let's think about what happens if you take multiverse ideas to their logical extreme. Level 1. Infinite space creating duplicate regions. Level 2. Eternal inflation creating bubble universes. Level 3. Quantum mechanics creating branching realities. Level 4. All mathematical structures existing as physical universes. Put them all together and you get something staggering. An infinite ensemble of mathematical structures, each containing eternal inflation, creating infinite bubbles, each bubble containing infinite space with infinite duplicate regions, each region undergoing constant quantum branching. The scope is almost impossible to comprehend. Infinities stacked on infinities, every possible reality, every possible variation, every possible mathematical structure, all existing simultaneously. This is the ultimate ensemble. Everything that can exist does exist. All possibilities are realized somewhere in the vast structure of reality. If this is true, it would mean existence is vastly richer than we ever imagined. But it would also mean we're infinitesimally insignificant parts of it. One brief moment, in one quantum branch, in one region of one bubble, in one mathematical structure among infinite others. Does this make existence more wonderful or more terrifying? Probably both. One question the multiverse doesn't answer is the nature of consciousness itself. Why does subjective experience exist? What is it like to be you? Having experiences, feeling sensations, thinking thoughts. This is the hard problem of consciousness, and the multiverse doesn't solve it. You can have infinite universes, infinite quantum branches, infinite mathematical structures, and you still haven't explained why any of it is accompanied by subjective experience. Maybe consciousness is fundamental, a basic feature of certain physical systems. Maybe it emerges from information processing. Maybe it's an illusion. The multiverse is silent on this question. But the multiverse does raise new questions about consciousness. When quantum branching occurs, does consciousness split? If so, what determines which branch your subjective experience follows? Is there a fact about which future you is the real you? Many worlds suggests there isn't. All branches are equally real. Future you is not one person but many, all with equal claim to being your continuation. This challenges our usual concept of personal identity as a single thread through time. In many worlds, identity branches like a tree. You don't have one future, you have many. What would this be like subjectively? The theory doesn't answer. It describes the mathematics of branching, but says nothing about the experience of being a consciousness in a branching universe. These questions sit at the intersection of physics, philosophy, and neuroscience. The multiverse doesn't resolve them, but it makes them more urgent. Here's a disturbing variation on the Boltzman brain problem. In an eternal multiverse, random fluctuations should occasionally produce entire universes that look just like ours, complete with all our memories and history, but which actually formed moments ago and will dissipate moments from now. These Boltzmann universes would vastly outnumber real universes that formed through normal cosmological processes. Just like Boltzmann brains, they're statistically dominant in certain eternal multiverse scenarios. This means that if the multiverse is eternal in the right way, you should expect to be in a Boltzmann universe rather than a real one. All your memories of the past would be false. The universe would be about to end. Your future would last only moments. This seems absurd. You have excellent reasons to think you're in a real universe, with a real past and a real future. So the fact that we're not in Boltzmann universes suggests something is wrong with multiverse models that predict them as dominant. This is taken seriously as a constraint on cosmological theories. If your theory predicts that most observers are in Boltzmann universes, it's probably wrong. Various solutions have been proposed. Maybe the multiverse isn't eternal in the relevant way. Maybe there's a mechanism that suppresses these fluctuations. Maybe we need to use different probability measures. None is fully satisfying yet. It remains an open problem. If inflation is eternal going forward in time, what about backward? Did it have a beginning? The Border-Guth-Vilenkin theorem says that eternal inflation cannot be past eternal. It must have a beginning. The inflating region must have a boundary in the past, either in time or in space. This creates a puzzle. What came before inflation? What started it? Why did it start rather than not start? Some cosmologists propose that the universe tunneled from nothing through quantum processes. The laws of quantum mechanics might allow universes to spontaneously appear from a quantum vacuum. Others think there might be a multiverse of inflating regions, with our inflation starting from some pre-existing state. Still others argue that the question of what came before might not make sense. Time itself might have emerged with inflation. Asking what came before time is like asking what's north of the North Pole. The point is that eternal inflation, while explaining a lot, doesn't explain everything. It pushes the question of ultimate origins back, but doesn't eliminate it. Let's seriously consider the possibility that multiverse ideas are a wrong turn, a detour in the history of physics that will eventually be abandoned. What would that look like? Probably something like this. Someone discovers a new theoretical framework that explains fine-tuning without requiring other universes. Maybe a unique theory that predicts all the constants from first principles. Maybe a mechanism we haven't imagined that forces the constants to life-friendly values. This framework would have to explain why space appears flat, which currently points toward infinity. It would need to account for the success of inflation without requiring eternal inflation. It would need to make sense of quantum mechanics without many worlds or Copenhagen collapse. That's a tall order. But physics has surprised us before. Relativity replaced Newtonian mechanics. Quantum mechanics revolutionized our understanding of matter. Maybe another revolution is coming. If multiverse ideas are wrong, future physicists might look back and wonder why we took them seriously. They might see the multiverse as our generation's ether, an unnecessary complication added to save theories that were incomplete. But they might also recognize that engaging with multiverse ideas, even if they turned out to be wrong, helped us think more clearly about fine-tuning, probability, and the nature of scientific explanation. Wrong ideas can be productive if pursued rigorously. They can lead to insights that survive even when the original ideas are abandoned. So, whether the multiverse is right or wrong, the journey of exploring it has value. So here we are. We've journeyed through the multiverse hypothesis from every angle. We've examined the physics, wrestled with the philosophy, considered the implications, and faced the uncertainties. The multiverse isn't established science. It's not proven like atoms or evolution or cosmic expansion. It's a serious theoretical possibility emerging from our best physics, making claims we cannot yet verify, but worthy of rigorous investigation. You now understand why physicists consider it, what the different versions propose, why testing is so difficult, and what the implications might be. You've seen past sensational headlines to the real arguments and genuine uncertainties. What should you believe? That's up to you. The evidence is incomplete. The arguments cut both ways. Brilliant scientists disagree, but here's what we can say with confidence. The universe is almost certainly larger and stranger than the part we can see. Reality extends beyond our observation. Whether that includes other universes remains uncertain, but the possibility is worth taking seriously. The multiverse has already enriched physics by forcing deeper thinking about probability, infinity, and the nature of explanation. Whether it's ultimately right or wrong, engaging with it has been productive. And it reminds us of something crucial. We're finite beings grappling with potentially infinite reality. We're temporary patterns asking eternal questions. We're tiny sparks of consciousness trying to illuminate vast darkness. That's the human condition. We don't know everything. We might never know some things, but we keep asking, keep wondering, keep reaching beyond ourselves. The multiverse might be real. It might not. We might discover the truth in our lifetimes. We might never know for certain, but we can wonder. We can reason. We can calculate. We can test what's testable and think carefully about what's not. And in that endless drive to understand, we find what makes us human. The universe we experience is real, regardless of whether others exist. Your life has meaning regardless of whether infinite copies exist elsewhere. Your choices matter, regardless of whether all possibilities are realized somewhere. The multiverse, if real, doesn't change fundamental questions of how to live or what to value. Those remain separate from cosmology, but it might change how we think about our place in existence. It might inspire profound humility about how little we ultimately know. It might spark wonder at the possibility that reality extends far beyond what we can ever observe. And wonder might be the greatest gift this hypothesis offers. Not certainty, but wonder. Not answers, but profound questions. Not an end to mystery, but deeper appreciation of how mysterious existence really is. Carry that wonder with you. Let it fuel curiosity and remind you that reality is bigger than we yet understand. Let it inspire you to keep questioning and seeking understanding, because that quest is what makes us uniquely human. We wonder, we question, we explore. The multiverse, real or not, is part of that reach toward understanding. The answer remains uncertain. The journey continues. And what a remarkable journey it is. Even if the multiverse turns out to be wrong, pursuing it has value. Science advances through both correct ideas and careful elimination of incorrect ones. Every wrong turn teaches something. Every failed approach reveals why that path doesn't work. The ether was wrong, but pursuing it led to relativity. Caloric fluid was wrong, but studying it led to thermodynamics. If the multiverse is wrong, future physicists will understand why, learning what observations rule it out and what better explanation replaces it. And the tools developed while studying it will outlast any particular theory. Better understanding of quantum mechanics, refined techniques for analyzing inflation, clearer thinking about probability all remain valuable regardless. The multiverse hypothesis is valuable, even if false, as long as it's pursued rigorously with genuine attempts to test and constrain it. Perhaps the deepest lesson is learning to embrace mystery without needing immediate resolution. The biggest questions might not have quick answers. Some might take centuries. Some might remain forever at the edge of what we can know. The multiverse teaches us to be comfortable with this, to hold possibilities lightly, to reason carefully despite uncertainty, to continue investigating even when definitive answers remain elusive. This is how science has always worked at the frontier. Einstein didn't immediately prove relativity. Darwin didn't instantly verify evolution. The best ideas often take decades or centuries to fully test. We're impatient. But reality doesn't owe us quick answers. Some truths reveal themselves slowly. Some might never fully reveal themselves at all. Learning to work productively in this space, to make progress without final answers, is essential for frontier science. The multiverse gives us practice in exactly this skill. Let's bring this all together. What should we take away from 2 hours of exploring the multiverse hypothesis? First, the universe is almost certainly larger and more complex than the part we can directly observe. Even if there's no multiverse, there are regions beyond our cosmic horizon we'll never see. Reality extends beyond our perception. Second, multiverse ideas aren't arbitrary speculation. They emerge from serious attempts to solve real physics problems. Physicists didn't want these conclusions. The mathematics led them there. That doesn't prove the ideas are right, but it explains why smart people take them seriously. Third, there are multiple versions of the multiverse idea, each based on different physics. Level 1 from infinite space, Level 2 from eternal inflation, Level 3 from quantum mechanics, Level 4 from mathematical structures. These are distinct hypotheses, not one monolithic claim. Fourth, if the multiverse exists, it has profound implications for identity, probability, and our place in existence. The paradoxes it creates are genuine philosophical puzzles, not just mathematical curiosities. Fifth, Most dramatic multiverse predictions are currently untestable. We might find indirect evidence or new ways to test underlying theories. But other universes themselves seem beyond direct observation. Whether this disqualifies multiverse ideas as science is debatable. Sixth, we should remain humble. History is full of ideas that seemed crazy but were true. Atoms, quantum mechanics, black holes. It's also full of ideas that seemed plausible but were wrong. Aether, phlogiston, steady-state cosmology. We won't know which category the multiverse falls into until we have more information. Finally, even if the multiverse is real, it doesn't change how we should live. We still experience this universe, this timeline, this quantum branch. Our choices still matter to us. Our actions still have consequences in the reality we inhabit. The multiverse isn't an excuse for nihilism. If anything, it might make existence seem more precious. We're here, conscious, able to ask these questions about the nature of reality. That's remarkable whether we're alone or surrounded by infinite other universes. Science is our best tool for understanding the cosmos, but it has limits. Some questions might be beyond scientific investigation. The existence of other universes might be one of them. That doesn't make the questions meaningless. We can reason about them, consider their implications, evaluate arguments, even if we can't do definitive experiments. The multiverse sits in that boundary region where physics, mathematics, and philosophy blend together. Maybe that's appropriate for questions about the ultimate nature of existence. The debate about the multiverse is also a debate about what we want from science. Do we want theories that explain observations in the simplest way? Do we want testable predictions about new phenomena? Do we want mathematical elegance? Different scientists value different things, leading to different judgments about speculative ideas. What matters is that disagreement is conducted honestly and rigorously. People should argue about evidence and logic, be willing to change their minds, and respect that smart people can reach different conclusions from the same information. The multiverse debate generally meets these standards. Yes, there are strong opinions and heated exchanges, but overall, physicists on both sides are genuinely trying to figure out what's true. That gives me optimism. Even if we never definitively resolve the multiverse question, grappling with it pushes our knowledge forward. We learn more about quantum mechanics, cosmology, and the foundations of physics. We develop new tools and frameworks. The history of science is filled with questions that seemed impossible to answer. How old is the Earth? What are stars made of? How did life begin? Each seemed beyond our reach at the time. Yet through persistence, creativity, and new technology, we found answers. The multiverse might follow a similar path. Right now, it seems untestable. But new technologies emerge. Theoretical insights open unexpected doors. What seems impossible today might become routine tomorrow. Consider that just over a century ago, we didn't know what atoms were. We had no quantum mechanics, no relativity, no understanding of cosmic expansion. We thought our galaxy was the entire universe. The pace of discovery has been staggering. Who knows what the next century will bring? Maybe we'll find ways to test the multiverse. Maybe we'll develop better theories that explain fine-tuning without needing other universes. Maybe we'll discover the question itself was confused, and the real answer is something we haven't imagined yet. That's how science works. We don't know what we'll discover until we discover it. Every answer raises new questions. Every solution reveals new mysteries. The multiverse might be one of the greatest discoveries in human history. a revelation that reality is infinitely larger than we thought. Proof that existence extends far beyond what we can observe. Or it might be a wrong turn, an idea that seemed promising but led nowhere, a reminder that even brilliant scientists can be led astray by elegant mathematics. Either way, the journey is valuable. The questions matter. The search for understanding is what makes us human. We stand in our universe, looking out at the cosmos, wondering what lies beyond. Maybe there are other universes, other versions of ourselves, other realms of being. Maybe we're alone in one single reality. We don't know. Maybe we never will. But we can wonder. We can theorize. We can calculate and reason and search for evidence. That's the scientific spirit. Not claiming certainty where none exists. Not giving up on questions because they're hard. Being honest about what we know and what we don't. Following evidence wherever it leads. The multiverse might shatter our assumptions about reality. It forces us to consider that existence could be far vaster than we imagined. But it doesn't break reality itself. Reality is whatever it is, regardless of our theories. What's changing is our conception of reality. That willingness to expand our minds, to question everything, is what science is about. The multiverse may be the next transformation, or it may not. Either way, the journey of discovery continues. We're standing at a frontier, looking into mystery. Whether the multiverse is real, whether we ever prove it, the fact that we can conceive it and reason about it says something important about human intelligence and curiosity. We're not content with easy answers. We push deeper, asking harder questions, venturing into territory where knowledge becomes uncertain. That's where we are. At the edge of what we know, looking out into what we might discover. The questions are big. The answers, if they come, will transform our understanding of existence. Until then, we wonder. We calculate. We debate. We search. The multiverse gives us plenty to wonder about. And in that wondering, in that questioning, in that persistent drive to understand the cosmos we inhabit, we find meaning regardless of what ultimate answers we might discover. You know more about these ideas now than most people ever will. You understand why physicists consider them, what the different versions propose, what the implications might be, and why testing them is so difficult. What you believe is up to you. Science gives us tools to evaluate ideas, but at the frontier, certainty fades. The multiverse remains what it's been all along. A serious possibility, a real scientific hypothesis, a window into how far human thought can reach when we dare to ask the biggest questions, whether proven or disproven. It represents something important about how we approach the unknown. We don't shy away from strange ideas. We follow logic wherever it leads. We take seriously what mathematics tells us, even when it conflicts with common sense. That's the legacy of this exploration. Not certainty about whether the multiverse exists, but a deeper understanding of the questions themselves and why they matter. Reality might be bigger than we thought. Existence might extend beyond all boundaries. We might be one small part of something incomprehensibly vast. Or maybe not. Maybe this is all there is, and that's enough. Both possibilities are worth contemplating. Both say something about existence, meaning, and what it means to be conscious beings wondering about our place in reality. The cosmos rewards curiosity. It yields its secrets slowly. It remains fundamentally mysterious, even as we learn more. That's not a problem. It's the human condition. We're finite beings contemplating the infinite, temporary patterns asking eternal questions, tiny sparks of consciousness illuminating vast darkness. And that's beautiful. That's what makes this journey worthwhile. Not the destination, but the journey itself. The wondering, the questioning, the search for understanding. The multiverse, whether real or not, is part of that search. It's us doing what we do best, reaching beyond ourselves, asking what if. And in that reaching, in that asking, we find what it means to be human.